This is a video for Edexcel Further Pure 1, Inequalities section 1.4, which looks at alternative methods for solving algebraic inequalities. In previous videos we've seen a standard method for solving inequalities involving algebraic fractions, where we found critical values and then looked at the regions that those critical values give us to decide whether the function is positive or negative. Alternative methods are available, and we're going to look at one of those, which is a graphical method. So for example, if we have 6 over x plus 2 greater than or equal to x plus 1, the method that we looked at before would combine these as a single fraction. However, what we can do is to consider it as two separate graphs. On the left hand side, f of x equal to 6 over x plus 2, and that is a reciprocal graph, and then on the right hand side, g of x equal to x plus 1, and that's a straight line. Now, both of these are relatively straightforward to graph. So we're going to do this on the next slide. First of all, let's consider the left hand side, 6 over x plus 2. This is going to be similar to the graph of 1 over x that you're familiar with, but because it's x plus 2, it's translated 2 units to the left. So in other words, the asymptote is going to be going through value -2. To the left of x equal to -2, the graph is in the negative portion, looking like this, and to the right it's in the positive y values, and we can look at where it crosses the y-axis. In fact, it will cross at a value of 3, that's 6 divided by 2 when x is equal to 0. Although for the solution that we're looking at, that's not really that important. So there's a quick sketch of the reciprocal graph. The straight line, x plus 1, well, that will cross at 1 with gradient 1, so it will look something like this. So there's our two graphs sketched, and what we want to know is when is f of x, the reciprocal, greater than g of x, the straight line. In other words, when is the curve lying above the straight line? Well, obviously it's from this point here downwards, and from the asymptote up to this point, so between these two values. So we need to find these points of intersection. In other words, we need to find when is 6 over x plus 2 equal to x plus 1. Now to do that, straightforward, we can multiply by x plus 2 when we've got an equality or we've got an equation. So that means that we have that 6 is equal to x plus 2 multiplied by x plus 1. Multiplying out the right hand side gives x squared and then 3x plus 2. And therefore, subtracting 6, we get that x squared plus 3x minus 4 is equal to 0. And therefore, we have that x plus 4 and x minus 1 is equal to 0. So our solutions to that are x equal to -4, in other words, this point here is that x is equal to -4, and x is equal to 1. So this is x is equal to 1. So let's look at that neatly done on a graph on the next slide. So there we have our values x equal to -4 and x equal to 1. Now the important thing then is to look at the solution. So we want from -4 downwards, and then between the asymptote, which is at -2, up to the point 1. But remember that the asymptote is not allowed, so that would be, if we're drawing it on there, an open circle going up to our point at 1. In other words, we have this solution: x is less than or equal to -4, union with x is between -2 and less than or equal to 1. So it's strictly greater than -2. -2 is a value which is not allowed in our inequality and therefore mustn't come into the solution. Now sometimes the graphs involved were not as simple as that, so we have an alternative method which is based on algebra rather than the graphing. And here's an example of that where we've got x plus 1 less than or equal to 2x plus 7 over x minus 1. Now we did meet this in an earlier video, and remember we did it by combining these as a single algebraic fraction. Now an alternative way is to do something about the x minus 1 by multiplication, but remember we can't simply multiply by x minus 1 because that is sometimes positive and sometimes negative, and we wouldn't know which direction the inequality has to be then. But we can overcome that by making sure that we multiply by something which is always positive. And one way of doing that is to multiply by the factor squared. And we know that for all values of x this is going to be positive. So what we're going to do here then is to multiply by x minus 1 squared. So the left hand side becomes x minus 1 all squared multiplied by x plus 1. Then we have less than or equal to 2x plus 7 multiplied by x minus 1. We can now subtract the right hand side from the left hand side. We get x minus 1 all squared, x plus 1 minus 2x plus 7 multiplied by x minus 1 must be less than or equal to 0. We can take out a factor of x minus 1, leaving in the bracket x minus 1 multiplied by x plus 1, so that's x squared minus 1, difference of two squares, and then we're subtracting from that the factor 2x plus 7. If we now look at what we've got in the square bracket, so that should be x minus 1 there, and then in the square bracket we have x squared and then minus 2x and minus 1 and minus 7, so minus 8. That's less than or equal to 0, and that factorizes two factors, x minus 4 and x plus 2. So we have x minus 1, x minus 4 and x plus 2 less than or equal to 0. Now this is a polynomial inequality that we've looked at in previous videos. We could do this by looking at the critical values and drawing up a table, or because it's a cubic here it's quite straightforward to actually look at the critical values and drawing a graph. So we have here the graph sketched. It's a cubic graph. We need the critical values, so we know that the point here must be at -2, and then we have plus 1 and plus 4 as being the critical values. Now we want less than or equal to 0, so we're from -2 downwards and between plus 1 and plus 4. But again we have to be very careful, don't we, that we don't include the value x is equal to 1, because that would be 0 in the denominator of our inequality, and it's not therefore defined at that point. So the solution is going to include -2, but when we look at the other side it's not including 1 but does include 4. So in set notation then we have the set of points x such that x is less than or equal to -2, union with the set of points x such that 1 is less than x is less than or equal to 4. So let's just look at that method. Again, we started off with our inequality, and by multiplying by something which we knew to be positive, in other words x minus 1 all squared, we managed to show that we had this polynomial inequality. We can solve that by looking at the graph or by drawing up a table of values, and what is vitally important is that we check these critical values very carefully, so that although the graph would seem to indicate that 1 is included, it's not, because we can't have x is equal to 1 in our inequality. For the graph, the polynomial there, that's fine, but for the initial inequality it isn't. So therefore we must be very careful not just to take the points from the graph, but to think back to the original question. Well, that concludes this video, and indeed includes the series of 4 videos on solving algebraic inequalities.